Ethers have the general formula of R, ROR. So we have an oxygen in the middle with the two groups attached to it. And to name them, we just name the groups on the sides, and then we follow that with the word ether. Cyclic ethers, though, are usually referred to by their common names. So we'll look at those here in just a second, but let's go back up to this. So we have two methyl groups on either side of this oxygen, so we call it dimethyl ether. So we know that both of those methyl groups on either side of the oxygen. Okay, here we have a methyl and an ethyl, so we call it ethyl methyl ether. And over here we have two ethyl groups, so we say diethyl ether. Okay, so again, it's known that that oxygen is in between those groups. And then the common names down here, I'm not going to have you memorize these, but you know, like I said, the cyclic ethers, we use their common names: ethylene oxide, tetrahydrofuran, and then 1,4-dioxane. So we won't really do a whole lot of that. If the group doesn't have a simple name, the compound can be named as an alkoxy derivative. So the alkoxy derivative is right here. So we can say OCH3 is called methoxy. OCH2CH3 is called ethoxy. Okay. So for example, over here, I actually have an alcohol. I have this OH group. So I would name this as ethoxy, and then I have 2 ethanol. Okay, and then we put the number in for the OH group. Here we have a phenol, and we have a methoxy. And then over here we've got 2 oxygens, so we can say dimethoxy, and then name the middle part ethane. So 2 ways here to name ethers. Again, you can either name the organic groups on both sides of the oxygen and then say ether, or we can use the methoxy, ethoxy groups. So ethers are polar because of the oxygen, but they don't contain hydrogen bonding like the alcohols and the phenols do. So because of this, they have higher boiling points than alkanes because of that oxygen, that polar oxygen. But they have a lower boiling point than alcohols. And we actually saw that at the very beginning of this chapter. Let's see here. Diethyl ether had a boiling point of negative 23 degrees Celsius compared to ethyl alcohol, which had a boiling point of 78.5 degrees Celsius. So boiling point is much lower than alcohols. Ether does have solubility in water compared to that of alcohols. So ethers are able to accept a hydrogen bond provided by water because of the unshared electron pair on oxygen. So it doesn't actually have hydrogen bonds on itself, but it can accept those hydrogen bonds from water because of the oxygen. Ethers have many alkane-like properties, and they do not interact with most acids and bases. They're flammable. So again, they have properties like alkanes. And then diethyl ether is the best known ether. So it was used as an anesthetic for years, but they found that it had a very long recovery time and it induced nausea. So it's been replaced with safer, less flammable anesthetics. And ethers must be stored without the presence of air, or they can form explosive peroxide. So you have to be careful with storing ethers. Okay, let's do some examples here. So I'm going to, whoops, not what I meant to do. There we go. I'm going to go to this page so I can draw these out for you. Okay, so first we have 2-ethoxypropane. So we're going to have propane 1, 2, 3. There's propane. And then we have ethoxy, so we have an oxygen with ethane pretty much attached to it. So that's what 2-ethoxy propane looks like. Okay, and then we have methyl propyl ether. So we're going to have a methyl group, then oxygen, and then propyl group. 1, 2, 3. So a methyl group on one side, propyl group on the other side. Okay, then we have 2,4-diethyl-4-ethoxyhexane. So this one looks a little weird. So I'm going to draw out the hexane. 1, 2, 3, 4, 5, 6. Okay, and then I'm going to put in the ethyl groups at 2 and 4. So I'm going to start on this side. So 2 right here, 3, 4. So those are ethyl groups. And then it says 4-ethoxyhexane. Okay, so we're going to put that right here. Ethoxy. Hexane. So that one looks kind of weird. Let me redraw this last one. There we go. That's a little better. Okay, now let's go back and name these. Okay, so the first one, we have OCH3 right here. So we're going to call that one methoxy. There's only one substituent on the ring, so remember we don't have to number it if there's only one. And then we have a ring of 5, so it's cyclopentane. Okay. This one here, I'm going to name up here. Okay, so we have another methoxy right here. And then we have propane right here. So this is going to be 2-methoxy, because that's our parent chain is the propane. So 2-methoxy propane. So you can number this 1, 2, 3, or the other way. Okay, last one, we have a methoxy group right here. And we have methyl attached to a benzene ring. So if you'll recall from chapter 2, that's toluene. So this is going to be, toluene is always, or the methyl group is 1, so this is going to be 2. So it's 2-methoxy toluene. Now we're going to look at thiols and disulfides. So thiol alcohols, or mercaptans, are sulfur analogs of alcohol. So an analog is just, has a similar structure to that of an alcohol. So instead of an OH group, like an alcohol, a thiol is going to contain an SH group. So to name thiols, you just add thiol to the parent carbon chain. So here's some examples here. So here we have ethane, and then we say thiol, okay? Here is our parent chain. So we're going to start numbering on the side of the SH group. So we have 1, 2, 3. So it's 3-methyl, 1-butane thiol. Okay, and then over here, again, we're starting the numbering by the thiol group. So 1, 2, 3. So this one's going to be 2-butene. So that tells us where the double bond is, 1 thiol. So instead of the OL that we were putting for alcohols, we use thiol instead. Thiols have a terrible odor, so it's responsible for the scent of a skunk spray. So that's pretty terrible. So the spray is actually contains, let's see here, it contains these two groups right here. So it has these in the spray. So that's why it's so stinky. It also is responsible for the scent of garlic and onions. I'm not sure why those are in the same category, because I like the smell of garlic and onions, but I hate the smell of skunk spray. So, and then it's responsible for the smell of a natural gas leak. So natural gas actually is odorless, but they put in the natural gas, they put methane thiol in, so that if there is a leak, you can smell it. So anytime you smell gas, it's that methane thiol that you're smelling, so you can detect the leak. So that's kind of interesting. Thiols can react with an oxidizing agent to produce disulfides. So here we have two thiols reacting. There's the oxidizing agent, and it forms a disulfide bond. So anytime you have sulfur bonded to sulfur, that's a disulfide bond. So that's the general formula there. Two sulfurs bonded together. Okay, let me give you a little example down here. So here we have CH3SH, so that's methane thiol, sorry. And then we have another methane thiol with the oxidizing agent. So remember that little O just represents an oxidizing agent. So then we get these hydrogens are removed. So these hydrogens here are removed, and we get the disulfide bond right here. So two thiols with an oxidizing agent will produce a disulfide bond. So disulfide bonds are kind of interesting. They're important in amino acids, especially cysteine, because cysteine contains a thiol. And disulfide bonds will occur between cysteines to help pull large proteins into shapes they need to be able to function. So just an example with hair, okay, they're rich in disulfide and thiol groups. So if you have curly hair, what's happening for those curls to happen is this oops, I went the wrong way. Is this disulfide bond right here. Now straight hair looks like this, where we just have the thiol groups. So that's kind of neat. But that's, this is basically what those disulfide bonds and large proteins are able to do, is pull these, make these curves in those proteins to be able to function. Okay, last part, and we've actually pretty much covered this already, but since it was in your book, I wanted to talk about it. So halogen-containing compounds, we've already been naming these. An alkyl halide is a compound that contains an alkyl group bonded to a halogen. So we've already been doing these. An aryl halide is a compound that has an aromatic ring bonded to a halogen. Again, we've already done those as well. We treat the halogen as a substituent, which that's what we've been doing, to the parent alkane, and the common names have the name of the alkyl group followed by the halogen name. So we have not used those names. Oops, there we go. So we haven't named them like that, with the alkyl group followed by the halogen. Thought I had an example here for you, and I don't see one. Let's see if I can find one real quick. Like methyl bromide. Okay, methyl bromide. Okay, would be CH3Vid4. That would be the common name for that. Okay. So we haven't been using that. We've just been using the IUPAC names, which is fine. So down here we have 1-chloropropane. So here's the longest chain in our compound, and we have chlorine attached to the first carbon. Here is our longest chain. Okay, so it's 2-bromo, 5-methylhexane. Again, we've already been doing it. And then this one, we have 3 chlorine, so it's trichloromethane. Halogenated compounds are used in a variety of medical and industrial uses, as well as industry and agriculture. So your book talks about, it's used as a degreasing agent or solvent. It's also halogenated herbicides and fungicides have increased crop yields. And then it says chlorinated insecticides such as DDT is responsible for control of malaria and typhus. So a little more of that is covered in your book, so read through that. And then the last part of Chapter 3 is stereochemistry, and I don't think I'm going to cover that right now. I think we'll come back to that in a later chapter, but we're going to skip it for now. So don't worry about doing those problems.